Our first speaker for the afternoon session is Alan Hayden. Alan is an ecologist and president of Natural Channel Design Engineering. He has been working with restoration of aquatic and riparian habitats throughout the Southwest for over 30 years. He's fortunate to work closely with engineers and hydrologists to develop geomorphologically and ecologically sound decisions for restoration projects. So join me in welcoming Alan to the stage.
I am an ecologist, and I do work for an engineering firm, which is an interesting mix of ideas. We are generally, most of our projects require, as Van said this morning, a lot of rednecks with big yellow machines. And that's generally how we go about planning our stuff. But over the years, and the years have added up, as Laura just emphasized, we have done a lot of what I call low-tech structures. They're low-tech, but they still require a lot of thought. And that's what I'd like to talk to you a little bit about today, is how to use geomorphology to make these things that are working so well and are so good to employ, make them last longer, and create less damage if they should fail. I just like to point out, and I point out in all my classes, that one of the first books written in history was Herodotus, and the first 3 chapters are about working with rivers and the mistakes that were made. And so this has been of interest for a long time, and there is a long history of failed channel improvements, well-intended, but not well thought out because they were not necessarily thinking about what the river required. They were thinking about more of what humans were trying to accomplish. And I think using a little bit of both can get us a long ways. So these hand-built low-tech structures are awesome. The ease of installation. It doesn't take much to teach people how to do this. They're relatively inexpensive. You can have very low impacts to the site other than what you're trying to achieve. You can do stuff with volunteer labor. There's an ease of permitting for this. And they are, as has been shown all over, are having a huge positive impact, okay? And there's no denying any of that. They do have a high failure rate, which requires frequent maintenance, and that can all be fine as long as it's part of the plan. But failures can create harm to the site and the resources that you're trying to protect or conserve. And, they do have some limitations. You may not be able to achieve all of the things that you would like to achieve from that site with these hand-built low-tech structures. But that's not to say we shouldn't use them, because they're pretty awesome. You can get an awful lot done on a big landscape and make huge differences in what's going on. And I think everybody in here that's done this kind of stuff sees that. So, one of the first things we start, and I work with the engineers, and we have a project. So what's the site look like? What are the issues? And then how do we put that in the context of what's going on geomorphically? And how can we achieve what we want to achieve ecologically? And then turn that into some engineering talk. So, we're talking about what are the functions that we're really trying to achieve? Are we trying to use grade control and arrest this active head cutting that's going on? Are we in a point where, we're looking at incision and loss of floodplain connectivity and that energy transfer that goes with it, and we're losing that wetland function? Or are we at a point where we're using, where we're seeing more lateral instability? It's stopped moving down. And we're looking at lateral instability and probably some sedimentation, those kind of things. And I like to always think of things in this form of Schum's model. This is this channel evolution model where things in size, then they get wider, and then they build their floodplain. And I think there's this, this is real. It goes on in a million different places, especially through the Southwest. And it's really good to understand where you are in this in this evolution, so that you know what you're trying to do. Okay? Are we trying to stop incision? Are we trying to raise that channel back up and get the floodplain back? Or are we just trying to stop lateral migration of the channel and arrest that kind of stuff? So that's how we kind of first form our geomorphic perspective. We then, once we know what those issues are and what we're trying to achieve with the site, then we start looking at, what is the appropriate structure. And these are low-tech structures. This is not moving the channel from one side to the other. This is how are you going to use hand-built structures with local materials and best achieve the results that you want to see. And that's what makes these things inexpensive and able to be repeated time after time after time. And that's what makes them easy to permit, both on forest, BLM lands, as well as if you're working in jurisdictional limits. So if you're using natural materials that are, if they fail, they're going to still be natural materials in the stream, you get less of a hairy eyeball if you're going in front of trying to get a permit to do this work. So there's a lot of different structures you can use, one rock dams, rock and brush structures, barbs, veins, all of these things can be built. And I will emphasize again and again, because I'm an ecologist, this vegetation, the bioengineering portion is really important. Most of the time, that's what people are trying to achieve, is to increase plant growth within these floodplains or in the channel. But you can use that vegetation, as I think was shown earlier today, to really help achieve those points. And I think the integration of all those things is really important, okay? There's a lot of materials that you can utilize. Wood, rock, vegetation, they all have their strengths and they all have their weaknesses. Wood is light. Hand crews can carry it around for the most part. It's oftentimes really available, okay? And in ephemeral systems like what we have here, it is short-lived. If you put water on it and keep water on it, it's really long-lived. And so the lifespan of those materials is really important to understand and make sure that they're going to last long enough to get you to your objective and help maintain that objective over time, okay? Wood is also harder to shape. It does not readily form a channel. It can be made to work, just takes a little bit more to work. Rock, heavy, not always expensive, sometimes really, or it's not always available, and when it's not available, it is very expensive. It has a very long lifespan, okay? And importantly, what we just learned last year is it does not burn, okay? Which is really handy in fire-prone areas. And it's pretty easy to create a channel out of that. Vegetation, my favorite, easily portable. We've just spent the last 2 years packing willow poles up to high elevations in the wilderness areas, easy to do, and we're using that material to help shape the channel and also to shape the channels to come. Talk a little bit about that later. And it can be self-sustaining with very minimal management, all right? So you need some water to make that work. But all of these materials are available to you, and all of these structures are available to you. But they should all be considered as in the context of what the stream needs to do and what you're trying to do with the stream, okay? And, make no mistake, you are manipulating a river or a creek, and that should give you pause. So, one of the first things to do is consider the sediment load, okay? There are lots of fancy ways to do this. It takes a lot of math, takes a lot of thought, but there's also some really seat of the pants things that can be done. And when we're working in an arid environment, like what's off here to the right, and we have steep eroding banks, not much vegetation, we can generally be sure we're going to have a sediment load. And that sediment load is going to be available to be transported in the channel, to fill our structures, to raise that channel if that's what we want to do. However, if you look at the situation off on the left, this is around Flagstaff, a site we were asked to go to because they were not achieving their goals. This is a degraded wetland. They built a beaver dam analogs. 5 years later, nothing's working. Well, they built beaver dam analogs in place, number one, hadn't had beaver in about 200 years, and will be another 100 before it does get there. And they didn't have the sediment load to fill the channel behind it. This is high elevation, spring fed, no eroding banks except for this one small incised channel. And so without that consideration, they were not achieving their goals, and they had chosen the wrong method to get there. And then this, consider the hydrology. And we are here in the Southwest, and a lot of this work is going on at fairly low elevations in the Southwest. And what I'd like to kind of point out is that up on the top, we have some ratios, and those are ratios of the bank full flows, that 1.5 to 2 year flow that does a lot of the work, to the much larger flows, the more infrequent flood flows that come along. And you'll notice up in the Salmon in Maryland, they're 2 times the 25-year flow, that 4% chance of occurring. It's maybe 2 times what the year and a half flow is going to be. However, if you get down to Arizona and New Mexico, those ratios change dramatically. And your structures are going to see an awful lot more water. And if you don't have a floodplain to arrest and spread out that energy, those structures are probably going to go away. And that is something to consider as well. These, in the upper Gila and the Salt, we're looking at a 4% chance of flow of 30 times the annual flood flow, okay? Probably 300 times the base flow. So when you are planning these things, please think about, the longevity of them, okay? That energy that's there is going to affect the material size and design, all right? Shear stress is function of depth, slope, and the weight of water. And what I've done here is just look at the competency of depth, slope, and weight of water, put it into grain size on the left side, and a 20-inch rock is about kind of what people feel comfortable carrying around. And if you look at the slopes and the depths of water where a 20-inch rock is not going to be mobile, that is fairly limiting. Okay, and should be a little bit sobering for if you are trying to make things last for a long time. Okay. In consideration of all that stuff, we have to start using geomorphology. Consider the shape and the elevation of your structure relative to the floodplain. You want to make these structures spread those flood flows out onto a floodplain. Here in Little Turkey Creek in the Gila, these structures were built to an elevation where they can spread things out really wide. And then down lower, down here on the right, we're looking at an incised geomorphic floodplain that is just enough to spread enough energy out that we can expect that structure to stay there and continue to do its work, okay? You want to place these structures in the appropriate channel location, okay? Keep in mind that streams, channels, form riffles and pools in sequence. And that riffle pool sequence is quite predictable, okay? You can go to a reference site and scale things up and down, you can look at your site and it'll tell you what's going on. And you can understand what that riffle and pool sequence is. And place your structures, because most of these things are going to be the riffles. They are going to be the hydraulic control. And you want to make sure that they are there doing what they're supposed to do. Don't place your structure in a meander pool like this and decrease the depth of the pool and decrease the amount of energy that pool is able to soak up. Okay? Choose the width of the structure with the function in mind. Okay? These on the left over here, these are supposed to spread flows out, drop sediment out, reduce that shear stress. Over here, they didn't take all that into mind. They didn't spread it out enough, but they spread it out enough to over widen the channel. And you see the channel width that was in place above, and see what the structure has done by over widening those flows and creating a plunge pool beneath. So we're losing the things that we were trying to save. Okay? Consider the energy the structure will create. Okay? You've created a dam and it creates a waterfall at the bottom. Okay? These structures here on the Pecos were over widened. They took out the banks, and after that, they started taking out the bed of the stream and have undermined and had to be rebuilt. And this was just 2 decades after they were built. So keep this in mind. Things can happen pretty quick. Take a long-term approach. And it's great to hear all the talks this morning, because everybody is taking a long-term approach. You don't have bulldozers, you don't want to use them, okay? Consider using that channel evolution model to set things in place. We just started a project in the Gila Wilderness where we can't use bulldozers, and we are rebuilding an incised channel that's wide enough to support vegetation, and then in 5 to 10 years, that vegetation will support beavers, and they will be reintroduced, and then those beavers can go ahead and finish the work and regrade those wetlands for us. Okay? So plan for these high discharges, use the native vegetation, and keep up all the good work. I really appreciate it. So, thanks.
We do have some time for questions for Alan if anybody wants to. I see somebody coming up to the microphone already. Thank you.
Well, it does my heart some good to see an ecologist in an engineering firm doing this kind of work in there, because I was the only ecologist in a civil engineering firm and also have been an advocate for things like this for years, and they're starting to catch on, and I love it. I have a project coming up that is in one of those situations where we need to raise the channel, but we have limited sediment and water to work with. And so you said the beaver dam analogs may not be the right approach. We are doing a major modification of that and some other approaches too, but I was curious what you think in that situation the best approach would be.
Well, I don't know where you are exactly, but if you don't have the sediment to fill the channel over the time period that you want, you could go upstream and create some sediment. That's easy enough to do, right? Or in many of those cases, we would consider maybe that is not going to be a viable option. Maybe you should move the channel to one side of the valley or the other and abandon the old channel, put the channel back on top, which is not really a low-tech solution. It can be done. Bill and Van have done lots of this stuff without using a lot of, without thousands of bulldozers, just one, and just plug that channel in multiple places as long as you have a place to put it and put it with an appropriate floodplain. So, and and then you can have potholes in your valley that were the remnants of your old stream, and you can fill that alluvium back up, if that makes sense.
We're realizing we are going to have to recruit sediment from elsewhere and put it in the channel. It's moderately incised in places.
Yeah. Mm-hmm. Cool.
Yes, absolutely.
Yeah,
all right, thank you.
It's a great problem. So, all right. Thank you.
Bye.